Okay, very good, very good. So today we will continue to complete our discussion on the direct method, and also we will start to talk to start the Unix bar discussions. Okay, so very good. So a few logistics things to update before the formal introduction of the materials. So firstly, the homework 0 and homework 1, we don't need to submit that we discussed already. And I have the solution of homework number 1 posted in Canvas already. So you can use that. Homework number 1 actually contains both direct method and Unix bar questions. So you can use that to solve corresponding questions for the materials we covered. And as we cover more and more, you are able to do more questions there until you complete all of them. And then we will post the homework number 2. And then from number 2 on, you will need to submit all the homeworks. And the TA has posted the way that how you submitted the homework. So everything should be in place. Okay, so make sure that you follow all those suggestions. Yeah. On Monday, next Monday, we will have a quiz number 1 for the class. This quiz question will be on the direct method. So we will have a simplified version of 1D Spring system, and then you will be asked to solve that problem. Okay, so you in the class I give an example about the 6 springs, right? So 6 springs, 5 nodes. So in the quiz we will have a simpler version. And then you can use the same principle to solve that. If you are able to go through independently the example I give in the class, then you should be okay. Okay, so make sure you do the exercises after the class. Okay, so that's quiz number 1. We will start at 1:15, around 1:15 p.m. So we will first have the lecture, and around 1:15 p.m. then we can have the quiz posted. Not posted. We also put it on the Canvas, as well as we can share the screen. TA will come to share the screen to you, and then you can work on the quiz. You can write it in the piece of paper, or you can type in the computer, and then finally convert it into a PDF, and then submit according to TA's suggestion. Okay, he said submit through the Canvas, then you can through the Canvas. That's better. Okay, and then TA will grade it and then post your scores. Okay. You will be able to see that very quickly. Do you guys hear me? Can you hear me, guys? Very good, very good, very good. So let me change to the laser point. Very good, very good. Excellent. So that's for the quiz. For the exam number 1, that will be Wednesday. So we will start. We will use the whole class to do the exam. So it will start at 12:50, and we will have 3 questions in the exam number 1. The first question will be the 1D Spring system. Okay, so if you can do the homework well, we have homework number 1. They have the 1D Spring system questions, and then in the class we have the example of 1D system question, and we all have answers for that. We have the solution for that. If you can do those questions, do those problems independently, then you should be fine. Okay, so this is one question. Second question will be mathematics, especially the eigenvalue problem, and we discussed about it in our class. We went through the examples, right? So make sure that you seriously, truly understand how to solve those problems. And then we will also ask some conceptual questions. So those are important concepts you need to understand. And then you can address them in a descriptive way, describe the terminology, describe the definitions that we have already explained in the class. Okay, so this will be 3 questions, majorly 3 questions, 3 problems in the exam number 1. So those are the key points I hope to list for you. So you make sure you when you review the material, review the lecture, you focus on those key points. Okay, but the other points they're relevant points. They're also important. Both exam and the quiz are open note, open books. You can open all those things. That's fine. Okay. So, but I really hope you not only copy paste things. You need to understand the concepts, and you are able to solve those problems individually, independently. Okay. So, can you guys hear me? Yeah. Excellent. Yeah. Most important is you can do it by yourself, because nowadays computer is so powerful. Many finite element question, you can model it in a computer, and then computer can automatically solve for you, get the strength deformation. However, if you don't have true understanding of the theory, principles behind the finite element, or underneath, which is those are the foundation of finite element. If you don't have those understanding, then you will not be able to interpret how the results can be used, right? So Mark Jason, yes, exam is open book and open notes, okay? And 10, yes, 10, yes, the e-notes also fine, yeah, fine. Mark and 10, do you hear me?
Yes.
Okay. Very good question. So that's clarify things. Okay. Yeah. Good. So that's for the quiz and exam. Let me turn off my video so that the sound may be more smooth. The bandwidth, we have more bandwidth. Okay. Good. Now you guys hear me, right? Yeah. Yes. Okay. Very good. Now, for again, these two are the logistics items we already discussed about, the Abacus video and also the guest lecture we already discussed about. We will stick to the plan. Okay. Very good. So those are the logistics. Since last class, actually, many students send me very constructive comments. I asked about 5 to 10 students. Actually, they in the class, they actually tell me that the pace so far we are following are very good. So don't be too fast, and the currently is fine. Only one student told me that the pace is slow. So do you guys feel the pace is slow? So far, I only heard one student give me very kind comment saying that the pace can be even faster. Do you think I can? Do you guys want me to be faster? Pace is good. Yeah. Okay. Very good. That's what I heard from about 5 to 10 students, right? So very good. So in this case, we will keep the pace the same as before, but let me know immediately when you feel pace can be faster or can be even slower. Okay, it's a very we will go in a bi-directional way. So if you have any feedback, let me know, and I will change it for you, and to let all of you have a great learning experience. Okay, if I myself have any questions, have any new things, new updates, I will let you know immediately as well. Okay, so let's go do it in a bi-directional communication. That will be excellent. Yeah. Okay, very good. So based on this this survey, we will keep the same pace. Okay. Yeah. Good. Okay. So here is the plan for the rest of September. So that's good. We are actually on the very good schedule. And the survey, yeah, feel free to send me your opinion, send me your comments after the class. Okay, so I will definitely incorporate your comments and concerns into the class to upgrade the class, so to let you have a greater learning experience. Yeah, good. Now let's get to the material we are going to discuss today. So in last lecture, we have started to assemble the individual spring conditions into the structure condition, right? So here, this is the spring constant, the spring system we have been working on for several lectures. Now you should be very familiar with the different components and different properties of each components. Here is a wall and a movable rigid body, springs, external force, right? And also the notation notation we use to denote the node, okay, and denote the element. So you need to be very familiar with those concepts. What is node? What is element? What is the external force? What is internal force? What is the displacement? Right? What is the Hooke's law? What is the relationship between internal force and the external force during the force equilibrium? Right? So those important key concepts you should be very, very familiar with. Now, to solve this system, we have been constructed the equation set for individual springs one by one, right? So, and then we assemble all those individual equation sets together to be a bigger one, right? So this bigger one, you see on the right hand side, this big one, it has a stiffness matrix here. This matrix is 5 by 5 because why? Because we have 5 nodes here. 5 nodes. It's not because we have 6 springs. 6 springs will be added into this 5 by 5 matrix. Okay, so this number, the dimension of the matrix is determined by the node. Why is determined by node? Because all the displacement are applied on the node. Displacement are from the node. All the force are applied to the node, right? So that's why we have 5 displacement, 5 force, and the displacement number will determine the column number. Force number will determine the row number of the stiffness matrix. And on the left-hand side, for the individual spring, we actually have stiffness matrix times displacement equal to force. Here we only have 2 because this is a 1D system. All the components are moving horizontally. So then we only have 2 nodes, and each node only have 1 degree of freedom around the x direction. So you have only U1, U2. And the force, accordingly, you have F1, F2, right? So make sure you understand all those notations here. And then the spring, and then for the stiffness matrix here, this is called the element stiffness matrix. Element stiffness matrix. Okay. When they are assembled together into this one, this 5 by 5 one is called a structural stiffness matrix. Structural stiffness matrix. Remember previously we said a KS, right? S can be a structure or sometimes called system, but usually called structure, KS. S is the subscript, right? KS. And then when we solve after we assemble them together, when we screw out some of the rows and columns based on the reason that the force is unknown, the displacement known, force is unknown, we rule that out. Then we will have a remaining matrix, stiffness matrix. That is called a global stiffness matrix. Okay, so these 3 stiffness matrix has different properties. They will come in a sequence. Okay, so now firstly we need to construct the structural stiffness matrix along with the displacement and force. So we have the equation, element equation of spring number 1 here, spring number 1 all set here. Okay. Last class we discussed how to write this, right? So this time I will not repeat it. And then you add this one into this equation, and then we do it in a sequence for the spring number 2. Number 2, it has the node 2, node 4, right? And then you add this accordingly into this structural matrix, right? And then this blue color shows the spring number 2. And then we do it in a sequence. Number 3, those are the red one. Number 4, those purple one. Number 5 are those green one, and number 6 are those brown one. And note, when you do this, you actually add the spring constant into the stiffness matrix. You will leave the displacement intact. because displacement are shared by all these springs. All these springs, when they move, because they are all connected with one rigid body, and then that rigid body has only one displacement. So all at that point, at that node, all the displacement are the same. So you won't change displacement here, but you will change the force. So those force are applied by those different springs, and they all contribute to the final force distribution of this rigid body. Okay, so force should be added, stiffness added, displacement not added. Okay. Now we talked about how to go even further. So once we have the equation set, then we look into individual every node. We look into that. We will see that each node is actually experiencing the force applied by the spring. Okay, and the force applied by spring actually is in opposite direction of the force generated inside the spring. Right, so this is always balanced at the node point. So then we need to add a minus sign for the force generated by spring, which we already derived before, FIE, right? FIE, right? That is the force generated on that end, one end of the spring, right? So now that force will be in equilibrium with the external applied force. So external applied force minus this the sum of all the force coming from the spring equal to zero. Okay, and then you can move this sum of the force to the right hand side. Here we discussed about the notation. E means the spring, so E equal to 1 to IE means the IE number of the spring. I is the node number in the system. How many nodes? Each node you have external force and the sum of internal force from the spring. And then these two actually are in the equilibrium. They cancel each other, right? That's why the whole system is in static, but the system is in stress. Okay, the spring is in stress, and the wall is giving the reaction force. So in this case, if we look at a specific example for the node number 3, then you will see F3 external force minus this minus 3 force coming from the spring equal to 0. Here, in last lecture, actually, after class, He Yang asked a question about the sign of this. You actually don't need to worry about the sign here. You assume we assume all the direction of the internal force from those spring is towards the left, and then external force F3 is towards the right. Okay, so because this number is given for sure, F3 towards the right, and the internal force is to be determined. We don't know, so we assume that all go in the left hand side to balance with external force. And then once you do this way, then this equation is reasonable. This equation is consistent because it's minus those force, right? And then you can calculate that. If you find in the results, if you find any force is positive, that means the direction we assigned in the first place is accurate. If you find the force is negative, that means the direction should be in the opposite direction from the with respect to the original assumed direction. Okay, so this is very straightforward. So just use this convention to solve the force there. Okay, do you guys hear me? Yeah, excellent, good. And then using the same convention, right? So then you can write you see the external force equal to the sum of all the internal force. And then when we add all those springs together, remember we actually have all the force from the spring added together, right? In the force vector. This actually means that they all equal. They are equal to the external force. They equal to external force, right? So that will be very, very convenient. So at each node, the summation of element force from the spring force is equal to the applied external force. Okay, so here I explained it clearly, but it will be better in the home. You can do it individually. Okay, you individually you test well, how can you assemble these things together. You should do it by yourself. Okay. this hands-on experience is very important. So do it by yourself. And then you see the equation, that assembled equation set becomes this way now. So on the left-hand side is the same. Right-hand side, you have all the external force applied. Some are reaction force from the wall. Some are no external force applied on the movable object, right? Movable objects. Yeah. So this equation actually is called a structural matrix equation. Structural matrix equation. So this stiffness matrix is called a structure stiffness matrix. Structure stiffness matrix. Okay. And they call it KS. KS. So this S is a structure. Okay. QS is a structure displacement for all the displacement in this structure, okay, or in this system. Force is all the force in the all the external force on each node assembled into a vector. Okay, so this equation is the abbreviation form of this this beautiful systematic equation, right? Okay, so for this structure matrix, it has a spatial properties. It is a square, right? 5 by 5 is square. Symmetric, because we add the symmetric element matrix into this matrix in a symmetrical way. We remember when we talk about the row and the column, for any matrix, any element or any spring, it has an element I and j. So when we add it into this structural matrix, we actually is the I column, j column, I row, j row, right? So that means they are symmetric when they add into this matrix is symmetric. So many of them added together, the result is still symmetric. Across the diagonal, the value is the same. And also this is singular. It is singular, okay? And it is a positive semi-definite. So this singular and positive semi-definite, the definition we already explained it, right? So those are the properties of this matrix. And here you see here we have two walls. On the wall, the reaction force is unknown, but the wall cannot move. So that means the displacement accordingly, like in this case 1 and 5, the displacement equal to 0. So the displacement is 0, and the reaction force are unknown, to be determined. Okay, that's always the case in solving those problems. The displacement is known, force is unknown. Force is known, like this other three. Displacement is unknown. Okay, it's always the case that you need to have only one, not two. Otherwise, you will get a conflict. Okay, so always keep in mind those principles when you solve those equations. So we also discussed an alternative way in last lecture, right? So go in a reverse way, not using the summation of different element matrix equation set, but start from the force equilibrium on each node. On each node, you have this force equilibrium equation, and then from there, each force we can write it in the form of Hooke's law that we discussed in the earlier class, how to write it. Every point, every equation is with respect to the node at that point, right? And then we can write all the force into this format. And then once we have this, you can extract U to be the displacement vector, and then you will assemble a new structure matrix. This structure matrix should be the same as this one. It's the same one. Okay, so you can play with it now after class, see whether you can get the same one. Okay, and the last lecture, I think Thierry asked the question about these two methods, which one is preferred. Actually, there's no preference. You can use either one. Either one you feel more straightforward, or either one, any one is more appropriate for the specific questions provided. Okay, then you choose any method, because final results will be the same. Okay, so there's no preference, so they are equal. Okay, good. Do you guys hear me? Yeah, excellent. Yeah, those are all very good questions. So I think you guys should ask more questions during the class. Then we can clarify things, right? We can clarify everything. And you when you do the problem set independently, you will further strengthen your understanding, right? So Once we have this, we will start to solve those solve those unknowns by imposing the boundary conditions. For this case, the boundary condition is on the wall. We already know what's the boundary condition, right? And the convention is when you add the number in, you have the number in the no number, right? The displacement U1, U5, force F2 to F4. The convention is you don't solve this one immediately. You scroll out some of the equation. You minimize the number of equation by rule out the one that has unknown on the right hand side, and then leave all the equations that have unknowns on the left hand side. You always do that. So in this case, two walls has no displacement but unknown force on the right hand side. So then we rule that out. Okay. When we rule out these two, then because the force 1 and the force 5 corresponding to multiplication of column 1 and column 5, right? So then these two columns also are not useful. So you can rule out that. Okay. So then you will only have a 3×3 matrix and a 3×1 displacement, 3×1 force. And the only unknown are the displacement on the left hand side. Force we already know. Spring constant we already know, right? The reason we do it this way is because this remaining matrix actually can be used to can be multiplied with its inverse and then become the identity matrix. And then the sign inverse can be multiplied on the right hand side. Then you can directly calculate what is the displacement. Okay, that's very easy to do, very easy to be operated in the computer in the mathematical way. Okay, so overall, to reduce the number of this equation, you follow this principle. You ignore the equation for which the right hand side are unknown. Okay, so all the unknown on the right hand side, those equations, you ignore them or you rule it out, and then strike it out the corresponding rows, and also in the same time eliminate those corresponding columns in the structure matrix that multiply into the zero values of the displacement of the boundary condition. Means this one, right? This column, because this value will multiply with U1, but now U1 is struck out now. So then you also need to struck out these two columns. So then we end up with a 3×3 global matrix. This is called global matrix now. Previous one, this one, 5×5 is a structure matrix, and 2×2, that is the element matrix. Okay, so now we end up with a global matrix, and then from here we have a K, Q is displacement, and F, right? And then this global matrix also has the property is a square, symmetric, positive definite, is positive definite, and non-singular, is not a singular. So the determinant of this one is not zero, non-singular. And then we want to solve the Q. We multiply, because this is a non-singular now. So it has the determinant, means it also has the inverse. So we multiply inverse K-1 on left-hand side, we get the identity matrix. Identity matrix times Q equals to Q. On the right-hand side, we have a K inverse times F, right? So overall, Q equal to K inverse times F, right? So this is very straightforward, very straightforward. So this is a very nice way to solve the equation. And once you have this, we will get the node number now, node number. And those node number, right? We have those node number. Once we have those node number, not node number, node displacement. We have the node displacement. Then each spring, we know the displacement because U1 and U5 is 0. U2, U3, U4 now can be solved from here. Then we know the displacement of any point, any node now, right? Any node. And then from there, we can go back to use the Hooke's law. We know the displacement, deformation of the spring. by knowing the displacement of both nodes, and then times the spring constant. That will give us the force, spring force inside the spring, right? So this is a very straightforward. Now you can know the spring force based on this information now, okay? And from from there, you can go back now. So you know this displacement now. You know U1, U5 now. So all the displacement we already know now. Multiply with this rho of stiffness spring constant, then it will give R1, right? And then multiply this column to last row, gives the R5 force, right? So then we will have all the unknowns solved. We know the displacement and the force. So then everything is solved. So that's the theory that you can follow to solve the 1D spring system. Now, we provide a specific example with a specific number. So for this system, we have the force given F3 here, 1000 Newton, F2 and F4 0 Newton. So no force actually is equal to 0. And we have 6 springs. Every spring, there are spring constants are given, Newton per millimeter. So those units are also very important. You should keep an eye on the unit. Some are Newton, some maybe nano Newton, some maybe micro Newton. Okay. Different unit, you convert all of them to the Newton, and then they can be compatible. Spring constant, the unit is Newton per millimeter, because it is the force divided by displacement. So it's the force divided by length, millimeter. Okay, you should keep an eye on this unit. Sometimes in the exam question, this is the meter, not a millimeter. Okay, and then you need to convert them to be consistent. Now here 6 spring, they have the 6 spring constant. U1, U5 we already know. Those are the boundary conditions 0, and then unknown is R1, R5, U2 to U4. Right now, once we know this number, and you firstly assemble the equation following the way we discussed. So they are all represented by the alphabet, right? Or by the symbols, all represented by symbols. Now, once this symbol is done, you are sure this is accurate. Now you can add the number in now. So once you add the number in, you add those spring constant in. You will have this equation, this matrix, and here only unknown is 3 displacement. Here only unknown are 2 unknowns are 2 reaction forces, right? So you have this. Now you follow what we discussed. Strike out the rows and columns. Okay, only leave with the global stiffness matrix, and this is the displacement, and this is the force. And then this one we can solve it. You know this value, and you can get the inverse of it, and then multiply it. Actually, here is also 3 equation set. Then you can calculate U1, U2, U3, U4. I saw some questions here. Emma, is this a good example for what an exam problem would be? Yes. Those are the example. Those are very similar problems we will ask in the exam problem number 1. Yeah, very good. And also the homework problem also has a similar 1D spring system. You also practice that, get yourself familiar with that. Thomas has a question. Is that 900 supposed to be 1200? 900. Let me see. You are talking about this one, Thomas? This one is 900. This should be 900. Let's see. This is the middle one, right? Middle one. Which number is this? K is this one. K3, K4, and 3, 4. Okay. Okay, maybe you are right. It's 1200. It's 1200. Yeah, this middle one is 1200. Yeah, we should change that. Yeah. Good. Very good. Very good. Very good. Very good. Good. Now, once we have this, very nice catch. Now, once we have this, we can calculate the displacement, 3 displacement. And then from 3 displacement, we can combine with the other 2 no displacement. Then we can calculate the force in each spring now, each spring. So each spring is a spring constant, corresponding spring constant times the elongation, right? So then we can calculate the P1, P2, P3, P4, P5, P6. Here, usually people write a P. Sometimes usually people write a F. Either way is fine, okay? Now, then we use those results. We can add back into the equation. So we have a previous equation. These 3 displacement we already know now, and these 3 force we already know. We don't need that anymore. So you can screw that out. Then if you rule out these 3, means the middle 3 columns in the stiffening matrix are not necessary anymore. So we remove that. So we only need 2 columns, two laws. Law 1 times this the displacement equals to R1. Law 5 times the displacement equals to R5. Then correspondingly, we can get the force R1 and R5, right? So by now, we solved all the questions. We get all the unknowns in this system resolved. So that's perfect. Okay. Now, overall, to solve this problem, as we discussed in the overall picture, if you want to solve a finite element problem, you start with remember we talked 4 steps. 4 steps about the for analyzing engineering problem. First, analyze the problem, and then you have pre-processing, like make a model and find out the material properties, and then you model it. You have for the finite element, you have different meshes, and then you solve the problem, and then you interpret the problem, and then if the problem converges, sometimes the problem you have a theoretical solution, the numerical the finite element simulation solution may not match with the theoretical solution. Then if they match, it's called converged. If not match, you go back to reanalyze the problem, get either the mesh size to be smaller or make the mesh organization to be more reasonable. Okay, so then you repeat this process, get it solved, and then during the core solve the problem. That's the thing we just discussed. When you have an element matrix, you have the system discretized into elements. Here, actually, this system is already discretized, right? As we said, it's already discretized. You already have the element now. So that means you don't need to worry that the discretization is reasonable or not. So you have this now. That's why you are in the step of solve the equation, solve the problem. So for that, for those elements, you first write their element matrix equation 1 by 1, and then assemble them together into the structural matrix equation set, right? And then based on the boundary condition, you can strike out some of the rows and columns following the principle we discussed. Then you get the global stiffening matrix equation, right? And then you solve that equation set using the way we just discussed. Then you get the results, right? And then you go to next process, next step of post processing, and then this steps is going on in a loop. Okay, so very good. So that's actually the end of direct method to solve any 1D spring system. But even this is simple. The meaning is very fundamental. You need to master this so that in next section we are going to talk about the uniaxial bar problem. The same principle can be applied there. Okay. Good. So here is one exercise. We have the solution for this exercise in the textbook. You see you have a 1D system, but now change a little bit as a vertical way, right? But the method is the same, and also it has a weight, gravity. So you see here, external force applied for this guy. External force is its own weight. Its own weight of number 1. Here is the weight of number 2, and then you have three nodes, 3 springs, right? And here on the top wall is giving a reaction force, no displacement, right? So this question can be solved. You can solve it independently after class, and it can be a very good practice. Okay, good. Now we can start to talk about the uniaxial bar element. Okay, so that's also a very important section in the class. Here now we step into this region, Okay, so what is uniaxial bar? Can you guys hear me? Yeah, excellent. So what is uniaxial bar? So uniaxial bar will be different from another very important concept that we are going to talk in the next section. That's called beam. Bar and beam are different. Bar usually means the objector, slender objector, thin objector is really thin. Okay, it only has, you can view it as a one-dimensional structure. So it is so thin, so it can only sustain axial force, only sustain the force around its length, around its axis. But the beam we are going to discuss in the future sections, beam is different. It's not that thin. Beam is not that thin. So for the beam, it's the cross-section area and the length sometimes is compatible, very similar. So that for the beam, they can not only sustain axial force, but also off-axial force. Means you can apply force perpendicular to the beam, and then that cause a moment, cause a torch to the beam. That is also fine for the beam. Okay, so step by step, let's first learn what is a bar first. Okay, to learn the bar, we need to first get familiar with some concepts. Previously, when we talk about a spring, it's very easy. Spring has only one spring constant, K. But for the beam, for the bar, the material, we need to consider multiple things. We not the spring constant of this bar actually comes from 3 important parameters. One is a cross-section area. One is its length. One is the material property of this bar. Okay, so for those bar, when they are stretched, or when they are pulled, they actually can get elongated. It's like this rubber band, right? Rubber band. The rubber band can be stretched, but it cannot be bended. Okay, so only stretch. For the bar, it can be stretched, can be compressed, but it cannot be bended. Okay, so when we talk about this deformation, usually we are dealing with small strain. Strain is a term that is equal to deformation of the material divided by original size of the material. For this bar, the strain is defined by delta, which is the change of the length, divided by L, which is the original length. Okay, so for the small strain, if for this ratio, if they are less than 0.5%, stress applied versus this strain is in a linear relationship. Higher strain, higher stress. Okay, and this relationship is known as Hooke's law. It's similar to F equal to Kx. F equal Kx, Hooke's law. But F in previously, F is force. X is displacement, the deformation. Here, stress is actually the equivalent to the rho of the force. Strain is equivalent to the deformation. Okay, and when these two divided, when these two are plotted, you will see for different material, stress versus strain, they have different slope. Higher the slope means stiffer are the material, and this slope is called Young's elastic modulus. Young's elastic modulus, because Young's is a very famous, very talented scientist, Thomas Young's. If you learn the optics before, you will know the interferometry that is developed by Thomas, and also in the mathematical calculus, he has made a great contribution in the mathematics. Okay, so Thomas Young, there's a book talk about saying the last genius. That actually is that means the Thomas Young. Okay, so when he studied the material properties, he actually find at this small strength, materials stress and strain has a linear relationship, and that relationship is called Young's elastic modulus. Okay, so here you see for the steel, Young's modulus is high, slope is high, right? Really steep. Plastic, little bit less. Rubber, even less. Gel, biomaterial tissue, even less, right? So they have different property. But this is only at a very small strength. If the strength is very large, they are not linear. They will not be linear anymore, and there will be some material memory get involved. So it will become more interesting, more complicated. Okay, so finite element can solve all those problems if the material can be have a complex behavior. Okay, but in the class right now, let's master the fundamental first. We assume all the material we are dealing with are elastic in this linear region. Okay, so once you know that the stress and the strain actually is proportional with each other and linked by the Young's elastic modulus, then we can write the definition of the stress strain there as well. Stress is defined as the force divided by the cross-section area of the bar, right? P over A is a force, is a P. This P, by the way, don't get confused. This P is meaning force, like the P we mentioned here, like this P, this force. It's not pressure. It's not pressure. Okay. So the unit of P is Newton, and then A is the cross-section area, and then strain is delta divided by L. Okay, delta is the deformation, net deformation. L is the original length and size. And then here you can write a delta. You can write a delta, move a delta to the left-hand side, and then put all other terms to the right-hand side. Then you will have PL divided by EA. PL divided by EA. Right. So why we write a delta? Why we extract delta here? Because this delta is a displacement. All the finite element question, when we solve it, we actually solve the displacement first, right? As we show in the previous calculation, we strike out the rows that has no displacement, unknown force first, and then leave unknown displacement on the left-hand side, and then we calculate that. Because from the displacement, you can calculate many things. Okay, from force, it's a little bit harder. From force to displacement, a little bit involves more steps. Now, once we have this, there is a principle of superposition really important. If you have multiple load applied to a subject, that subject will have one final displacement, but that one final displacement is contributed by the individual displacement coming or resulting from individual force. So if we have an individual force Pi, I is the individual number, Pi is a force, and then they apply to the object or different object joined at one node, and then they apply that every force contributed to one delta I, and then all this delta, all the displacement can be added together to be one displacement. Okay, can be one displacement. So that principle is called a superposition. Okay, this is a very useful one. And in terms of this Young's modulus, as we discussed in the last lecture, biomaterial have really unique those displacement, those Young's modulus, right? And the appropriate Young's modulus, appropriate mechanical property actually can also trigger cancer cells to migrate, to start to invade, to become invasive, malignant, right? So that's why the Young's modulus, this terminology is so important. So now we can start to look at it into the uniaxial bars definition. So I think now is a very good starting point. So right now it's 1:40. We can stop here. In next lecture, we will talk more about the uniaxial bar and have a detailed derivation. Okay. Let me see a question from Morgan. Does this mean for the course we want to be dealing with nonlinear relation? Yes, yes. We will not deal with nonlinear. We will not. Yeah, very good question. Yeah. Okay. Thank you, guys. See you guys. Very good.